Thanks a lot. It's a great honor to be speaking here, and I would like to thank Claire for inviting me. Okay, so I will speak about joint work with Radu Laza. Okay, so I'll start with saying something about the period map for quartic surfaces in P3. Okay, so I'll consider the geometric invariant theory, moduli space of quartic surfaces. So this is just projective space of degree 4 divisors on P3 modulo the action of PGL4. Okay, so this is moduli space of quartic surfaces in P3. This, I'll explain later why I'm using this notation. Anyway, this is the dimension. It has dimension 19. And we have, so we want to look at the period map. So there is a relevant period space. So this is a locally symmetric variety. Maybe later I'll be more explicit. And it has its Bailey-Borel compactification. Okay. The Bailey-Borel compactification. Okay, so we have this period map which goes from this GHE moduli space to, let's say, the Bailey-Borel compactification. Okay, and so this is birational. Birational. So this is global Torelli. But it is far from being an isomorphism. Far from being regular, even regular. Okay, and so let's give a quick look at the indeterminacy locus of this map. Okay. Okay. So let's describe some of the what it looks like. So there is one point which represents the tangent developable of a rational normal curve of degree 3. Okay, so okay, so this is in the indeterminacy locus, and this is an isolated point. Okay. Okay, and then, well, let me give you some. So we have one point representing a double smooth quadric. Okay, twice a smooth quadric is a strictly semi-stable point. And then we have, this is in the closure of a curve parametrizing quartics which are made of two quadrics tangent along a conic. So something like that. Okay. Pardon? Well, I guess. You mean this one? Well, it comes out of the analysis of GIT semi-stability, which was done by Chaire at the beginning of the 80s. So, 35 years ago, Chaire analyzed stability for degree 2 K3s and degree 4 K3s. Yes, you can apply a result of Luna. The stabilizer is, as Radu said, if you apply a highly non-trivial result of Luna, you'll see that it is. You'll see also that it has closed orbit in the semi-stable locus. And then there is this, so these are tangent along a quadric. Okay. And then you'll have this. In turn, this curve is contained in the closure of a locus parametrizing quartics which have a cusp curve along a conic, and so on. Anyway, it has quite a complicated structure. In fact, it's this joint union of this point and an irreducible subset of dimension, I never remember, I think maybe it's dimension 8. Okay. Dimension 8. And the sort of the most general point has an E12 singularity, isolated. So this is an isolated singularity. Okay. So it's something which locally in analytic coordinates looks like that. So my point here is simply, for what we'll see later on, that the indeterminacy locus is quite intricate in this case. This is why I'm listing some cases. And so a naive problem that you might ask is, just to formulate it in a naive way, is what happens to... Okay, so of course this period map, I didn't say it, of course it's clear to everybody. If this is a smooth surface, we just map it to the primitive H2, Hodge structure on the primitive H2. Okay, and so one naive problem one might ask is, what happens if I take a generic arc ending into this point or to this point or to a point on the red line and so on? So what is image of generic arc through the indeterminacy locus? Or maybe a more precise question is to decompose this period map as a composition of simple birational maps like flips or divisorial contractions. Okay. Okay. So now so at this point, let me give you what is Loyenger's point of view on this kind of problems. Okay. So, yes. Maybe vision is not, I don't know if it's proper. Okay, so I'll explain. So this is, what I want to explain is something which can be can be implemented in many circumstances. When we have the period map for polarized K3s, but it could be a hypercalars or similar varieties. But I'll explain it looking substantially at this case. But it has. So what we have here, if we look at quartics with ADE singularities, they're all stable. Okay. So they give me an open dense subset in the GIT moduli space, and the period map gives an isomorphism between this open subset and a certain open subset of the period space. Here I'm not compactifying because these will all land into the thing. And what we are missing are exactly two Noether-Lefschetz or Hergner devices, however you want to call them. So what are these? These are exactly the periods of hyperelliptic quartics. Hyperelliptic polarized quartic K3s. Pardon?
What is a hyperelliptic? Yes, it's a double quadric?
Yes. I was going to say in a second. Yes. So what this means is, so what I mean to be precise, these are hyperelliptic polarized K3s of degree 4 with the property that if you look at the map associated to the complete linear system, it's a double cover of a quadric. Okay? So what that means is that this is this goes into a quadric, and this is 2 to 1 onto a irreducible quadric. Of course, it's irreducible, but it can be either smooth or a quadric cone. Both cases occur. Okay, and these are the periods of unigonal. It's always polarized K3s, polarized quartic K3s. So here, one risks confusing everything. I mean, on one side we have quartic surfaces in P3. On the other hand, we have polarized K3s of degree 4. So these are different moduli spaces, of course. Otherwise, okay. And so unigonal just means that we can write the polarization is equivalent to a smooth rational curve plus 3 times an elliptic curve. So what we have is something, this is our S, this is our X, and we have a rational curve, and here we have our E. Okay? So this should explain everything. Okay.
You got me confused. I mean, wouldn't you need to take out something in terms of periods on the right-hand side? So wouldn't you need to describe these Hegel devices in terms of periods?
Yeah, no, I'm saying this is the set of periods of hyperelliptic quartics. And this is the set of periods of unigonal quartics. So I'm saying if I take out the periods, these two Hergner devices, what is left are exactly the periods of, by Meyer's results. If you have a polarized K3, so you should start with something with AD singularities to be precise. So, but anyway, you look at, of degree 4, you look at the linear system, it's either of this type or hyperelliptic, or it gives you, or it's an isomorphism to P3. It's better to think of the K3 as already something with AD singularities, and H is really ample.
But can you also describe them just in terms of periods? Like
Sure. No, that's what's in Kessel. Sure. Of course. Sure. I wanted to be more dramatic, but of course, and this is, I was going to say it. Yes, it's written here, right, the next line. Okay, so in fact, that's what I need to say. So those two Hegner devices are exactly described as follows. Okay, so, but first, so what Loyenga does, he says, okay, so all the problem, sort of, these are not the, I mean, that GHE modular space is not exactly this. I mean, you see, this is missing. So let's look at these two devices, but actually let's look at the inverse images in the, I mean, this is a quotient of a type 4 boundary symmetric domain by an arithmetic group. Okay, so let's look at that. And so what we have is we have this D19 modulo this. So now I'll explain. This is my f of 19. It's the quotient of a boundary symmetric domain by an arithmetic group. Okay, so if you want, this is, maybe I shouldn't write this. Anyway, this is a P21. This is a P20. And this is an open subset in the classical topology of a smooth quadric in here. And this is the quotient map. Okay. And what happens if we look at the inverse image in here of these two missing devices? This is exactly, so the inverse image, so this stands, of course, for hyperelliptic and this for unigonal. And so this is the union of the perpendicular V intersected D19, where V runs. So this makes sense because I told you that this, yeah, this is the, if you want, this is U2, this is the primitive, I mean, you take the K3 lattice, you take a vector of square 4, and you look at the perpendicular. What you get is this. This is the hyperbolic plane. This is E8 with negative definite, E8. Okay, and you want to look at things whose square is -4, and the divisibility is 2. So that means this is not a unimodular lattice, and so you can very well have a vector, a primitive vector, as this has to be, such that when you take the product with all elements, you don't get z, but you get 2z. Okay, and so this is the description Daniel was asking for. And this has a similar description, same thing as before, but now the divisibility is 4. Okay, this is z with q of 1 equal -4. Okay, so this would be a typical vector that gives me this. Okay, so now what does Loyenga predict? He predicts that the if you want to know, if you want to answer these questions, and or at least initially, if you want to know how complicated this period map is, you should look at these hyperplane arrangements. So what do I mean? Each of these perpendiculars is actually a hyperplane cutting this open subset of a smooth quadric. And so you can ask yourself, so this breaks up into this union, this infinite union of hyperplanes, hyperplane sections of a quadric. And you can ask yourself, well, do any of 2 of these hyperplanes meet? Do I have 3 of these hyperplanes meeting? And so on. So Loyenga predicts the pair map, let's say, intricacy, I don't know how to say this, of map linked to how, let's say, deep the above hyperplane arrangement is. Okay, so this might sound mysterious. I'll give you a few examples to explain what this is, what I mean by this. So let me give you 2 examples where Loyenga's prediction is completely is accurate. It's completely examples that confirm Loyenga. So the first one is you look at the modular space of degree 2 K3s. So you want to have something similar to what I had here for Quartic. So you have a GIT modular space, you have a period space, and you have a period map. Okay, so degree 2 K3 is generically it's the double cover of a plane branched along a sextic. So we take the modular space, the GIT modular space for sextic, plane sextics. And we have a period map to the relevant period space, which okay, I put the group on the other side. Okay, so so now the group, of course, is different. The period domain is always, I mean, the type 4 bounded symmetric domain is always the same, but what changes is the group. So so what is this? Let me write it this way. Okay, so this is the group, and if we do, so here there is, okay, so there is an analog of, I won't get into the details, okay? But anyway, what is the consequence? Let's call it H. Okay? It's a certain Noether-Lefschetz divisor. But now, if we do the inverse image of the relevant Heegner divisor, as we did here, then in this case it's smooth. So there are no 2 distinct hyperplane sections which meet. Smooth. Okay? So what Loyenga would predict is that the period map is quite simple. And in fact, there is a unique point in the indeterminacy locus. Okay? Only one, it's the 3 times a conic. Okay, and so now, what if we, if we look at the inverse of the period map, let's describe it through the inverse. So P inverse, how do you get this? Well, you do a Q factorialization, but I want the Bailey-Borel, okay? So what will happen is that this Heegner divisor, as all Heegner divisors, is Q Cartier before I take Bailey-Borel, but in this case it is not Q Cartier on the Bailey-Borel compactification. There is a Q factorialization of this Bailey-Borel compactification, and first you do this Q factorialization, and then there is a simple divisorial contraction, and what you get is this. Okay? So, so first you do this, and then you do a divisorial contraction. And now, there is another example, but I'll be really quick, is cubic fourfolds. Okay, and now it's the Morra space is something similar. Now it's a 20-dimensional type for monosymmetric domain, but the group is something similar to this. Okay, maybe there's a stable orthogonal group. Okay, and you have a relevant, the analog of these Hegner devices, and what you get here is, I'll just say it in words, what happens is here it is no longer smooth, this is no longer true, but at most you can have two of these hyperplane sections which meet. So you get the next step. It's not smooth, but you cannot have three different hyperplane sections in the monosymmetric domain meeting, but you can have two, and correspondingly you have to get the inverse. If you want to decompose the inverse of the Pearl map as a composition of simple things, first you have a Q factorialization, then you have a flip, and then you have a divisorial contraction. So the idea is that each time you add one intersection, if you have more, if you have three of these hyperplanes meeting, you would expect that you have two flips. If you have another, and so on. Okay? Yes, I mean, Lo-Yenga's idea is that you should start blowing up the locus where you have the biggest numbers of hyperplanes meeting, and then in some way you can contract that and you can go on. Exactly. Exactly. But it doesn't always work. Okay? Yes. So in fact, for Quartic, it doesn't exactly work this way. So okay. So, and so for this, I'll introduce, so now I'll explain why F19. So now back to, if we go back to Quartic, what happens is that, so according to Lo-Yenga, so let's follow Lo-Yenga, and we should look at this pi inverse. So as usual, we have pi is the quotient map for this gamma 19, and we should look at what I just erased. Okay. So I had these conditions and these. I'm sorry. Okay. Those conditions that I erased. Okay. And now, so this is smooth, no problem. And no hyperplane section here meets a hyperplane section here. So, but here, on the other hand, so these do not intersect. But here you can have as many intersections as you want. So you go down to point. So up to 19 hyperplanes, distinct, linear and independent, okay? With non-empty intersection, okay? So from Loyenga's point of view, this is as complicated as it can possibly be. And so let me give you a description of these multiple intersections. Pardon? Why this is, no, I mean, this is just an arithmetic computation. You see that if I have a vector of square minus 4 and divisibility 4, and a vector of square minus 4 and divisibility 2, there can be no point in D19 perpendicular to both. It's just an arithmetic computation. You have to use, you have to use the fact that, you have to use the signature of the quadratic form. Okay, so this is the reason so I want to describe this, these multiple intersections, but let me describe them, their images in the period space, okay, because that brings in a series, an infinite series of these locally symmetric varieties. And some of them, not only this 19-dimensional one, some of them have geometric relevance. Okay, so in order to describe these kind of things, introduce this D series. So what I mean is I want to look at a certain lattice, okay? So this is two copies of the hyperbolic plane, and this is the negative definite D lattice, the root lattice given by D, okay? 3. So if n is 19, this is isomorphic to what we had before, okay? So that's why it's relevant here. And I'll consider an arithmetic group which is essentially, it's just the O plus of this lattice if n is not congruent to 6 modulo 8. Otherwise, it's something intermediate, but never mind, okay? Between this and the stable. It's not here, it wouldn't make any sense to define it. And we want to consider the corresponding, okay, so dn, of course, is just, it lives, okay? So it's the corresponding type for bounded symmetric domain. So as usual, we want sigma squared to be equal to 0, and this, and we take one connected component. Okay, anyway. And now we want to take this dn modulo the action of this arithmetic group. Okay? So as I said, f of 19 is the one we considered. Period space considered, okay, before, up to now. If you look at f of 20, this is the period space of double EPW sextics, okay, modulo a natural involution, okay, or if you want, it's the period space for EPW cubes, whatever that means. And f of 18, this is the period space of hyperelliptic degree 4 polarized K3s. Okay, and now what happens is that, you know, we have an inclusion. If we look at these lattices, we have an obvious inclusion like that, because dn minus 2 has an obvious inclusion in dn minus 1, and so on and so on. So that gives us f of 3. This has dimension n, okay? Okay, and so on. So we have this infinite series of locally symmetric varieties, one included into the next one. And what happens is that now if you look at F19, these are exactly, so this is the hyperelliptic Hegner divisor, what caused all the complications in the period map. And then if we look at f of 17, this is exactly the image of you know, points where you have two distinct vectors of that kind intersecting, and so on. So then F16 is exactly where you have 3, and so on. Okay, so you see that you get this, you have as many, then of course you can continue and see that you actually can get up to 19, but this is a uniform up to 3. Okay. Okay, so the point I wanted to make is that here we have this series, and what I'm going to say for quartics in some way should apply also to moduli of hyperelliptic quartics, but more interestingly to the periods of double EPW sextics, and who knows, maybe there's one higher which has a geometry. So this is the point of introducing this series here. Okay. But now, at this point, I will, so if you remember at the beginning, I told you the indeterminacy locus for quartics has dimension 8. But if Loyenga rules, since here we get all the way down to 1 point, we would expect that the indeterminacy locus is a divisor. We should expect that it's actually even bigger. It has even a bigger dimension. So it's accurate in the case of quartics. In the dimension of the indeterminacy locus should be bigger than, be as big as possible. Well, of course, you cannot have a divisor as indeterminacy locus, but in some way it should be a divisor. So this is not true, I mean, because the dimension of this indeterminacy locus is 8. And, I mean, the moduli space has dimension 19. Okay. Sure. Yes, yes. Double EPW. Yeah, yes, because so yeah, if you look at polarized hypercalus of type K32 with a polarization of degree 2. That is the generic one. The general one is a double EPW sextic. But you get a divisor in this moduli space parameterizing HILP2 of a quartic, where the map is given by just given a subschema of length 2 of this quartic in P3, you get the line through these 2 points. So you have a map in P5 through the Plucker embedding. And that is, so the pullback of the Plucker line bundle is a polarization of degree 2. And there, it's not a double cover of its image. The image is simply a quadric with multiplicity 3 in some way. I mean, so that's exactly, you see geometrically where they come from. And so that's those are quartics, so it's the period space for quartics. Okay, so now so we're looking, so the question is why is Loyenga not so accurate in this case? So I want to at least get to what our predictions are for the decomposition of the period map as a composition of simple things. So in order to do that, I quickly want to take a slightly different point of view, okay? And then I'll give you our predictions and the explanation together of why Loyenga is not completely accurate this time. Okay, so let's give a slightly different reformulation of our problem. So, so let's look at this Q divisor class on the period space for quartics. Okay, and let's look at, this is the Hodge, orbifold, if you want, line bundle on F19, or the automorphic, if you might call it the automorphic orbifold line bundle. And, and let's look at an ample line bundle on the GIT moduli space of quartics in P3. So the GIT moduli space is the quotient of a projective space modulo PGL4. So the hyperplane line bundle on the parameter space for quartics descends to a Q line bundle on the GIT moduli space, okay? Ample Q line bundle on M19 descended from, let's say, O of 1. Okay. And now, if we look at the inverse of the period map, but let's just look here, because this is Q factorial, okay? So we're taking the inverse of the period map, but we're restricting it. We are forgetting about the boundary of Bailey-Borel. And what happens if we pull back this ample line bundle? If we pull back L of 19, we will get lambda, we'll get the Hodge line bundle plus delta of 19. That's why I put the 1/2, okay? Well, I mean, the 1/2 is there, well, because these are reflective Hegner devices. But, I mean, Anyway, okay. And on the other hand, so okay, on the other hand, F, the Bailey-Borel compactification, is a product of the ring of sections of the Hodge bundle. Okay. Okay. So if you take product of this, you'll get Bailey-Borel. If you take product of the ring of sections, you take all powers of this thing on f of 19, you will get this moduli space. Okay. So this gives you this, and this gives you, well, with a star, with the Bailey-Borel compactification. Okay? So at this point, it's natural to say, well, if I want to analyze this period map, I should just go from lambda 19 to lambda 19 plus. So we want to consider okay, and we yes, and we want to see the various birational models we get by varying beta. Okay. Maybe something like this. I don't know. So we want to take proj of the ring of this. Okay. So to get from one to the other. Okay. And so let's assume that they all finally generated rings. Okay, so we want the critical values of beta. So where does the isomorphism type of where does the natural map, it's no longer an isomorphism. Where do these projective varieties jump? Want Mori chamber decomposition, okay, of this segment. You start with, so you want to find what are the critical values of beta, okay? And so I'll write down what our predictions are, and then I'll try to explain why. Okay, what is the explanation for Loyenga's failure? Okay, let's say it brutally. Okay. So these predictions, the same method applies for any n, but I'm just doing it only in this case of Quartics. Okay, there's a jump of 1 over 8 is missing. So we get 8 of these non-zero critical values, which should correspond to that dimension 8 or something. Okay, that we had before of the indeterminacy locus. Okay, and so as I said, similar predictions for f of n. Okay, so the predictions are about these critical values. Of course, for large n's, we have no GIT moduli space to compare with. Okay, But in this case, this extreme value is a GIT moduli space. It would be the same for n equal 20, for n equal 18. So, okay. Now, so now I have roughly 10 minutes. So I would like to do two things. Explain what is our explanation for the fact that the indeterminacy locus has dimension 8 and not bigger, and two, that we actually have evidence in favor of these predictions, because you might think we are sort of, okay? So, okay. So, what is happening? Okay, so we are considering this kind of Q divisor on the period space. And so, see, this is globally generated away from, I remember, this is globally generated away from the union of these two devices. And all the problems really are here. I tried to explain this. So what we should do is restrict this to the hyperelliptic period space and see what happens. When I vary beta, it might go from being ample to being non-ample and so on. So we would detect these critical betas. And so, but if you start doing that, you will see naturally that that chain that one considers exactly because of Loyenga's vision, all of these terms will become involved. Okay, you restrict here, but then, so I'll write directly, so what I should do is restrict to any of these elements of this chain. Okay? And if one does some computations, one gets that this, if we restrict it to f of 19 minus k, this is 1 minus k beta times lambda. So this is the Hodge bundle here, a natural notation, plus 1/2 beta. And then we have the hyperelliptic. So this was defined, as Daniel asked, this was defined in terms of just arithmetic. And so the same definition makes sense for any n. Okay. So if you don't look at this term, you would say, well, as I go through 1/k, this will change sign. The restriction will change sign. So that would be exactly the kind of prediction Loyenga has. So that prediction will be that the critical values will be 1/k for k going from 1 down 1/2, 1/3, up to 1/18 or something like that. Okay? But this is here, so you can't completely disregard it. So the idea is that in general, as in the case of k equals 0, this should be some divisor which doesn't move, or actually it's birationally contractible, so that in some way the same argument works. But the fact is that some relations between the Hodge bundle and these Hergen divisors, which is derived from Borcher's famous automorphic form, give you that for high k, eventually this will become ample. So that screws everything up. So let me say, if this thing here in some way negative, then critical B's are 1, 1 over 2, 1 over 3, all the way down to 1 over 18 or something. Okay? But so let's say I'll just write one such relation, which was this was actually computed by Gritsenko. And similar relations coming from Borchardt. So this, if you feed this into here, you'll see that exactly this thing that you stop. I mean, I don't want, if I try to do the computation on the blackboard, I'll certainly mess it up. But so this, the consequence is that you stop, well, at k equal 9. I mean, there's some complication. I mean, you have to use these other relations. But that's the fundamental reason why, well, this is our explanation. We can't prove that all I said is correct, but we are not completely foolish. In fact, before finding the explanation, we had evidence from the GIT of quartics and even, I think, more striking, the GIT for hyperelliptic polarized K3s of degree 4. So, so the evidence, so there is evidence coming from GIT of quartics, but maybe I'll stress the evidence coming from hyperelliptic degree 4 K3s. Okay? So what I mean is the following. So what do? So as I said, we have analogous predictions for all n. So I wrote down the predictions for n equal 19, but we have predictions for f18. Now, if you want the analog, the strict analog, you should find a GIT moduli space, which is that. And so this is this moduli space. Okay, so this is the moduli space. You want to look at 4 curves on a smooth quadric, modulo the automorphism group of P1 cross P1, take the GIT moduli space, and look at the period map to the corresponding period space, which is simply the hyperelliptic divisor in the previous case. Okay? But now the nice thing about this is you can put this GIT moduli space inside, it sits naturally inside a series of GIT quotient, so you can do a variation of GIT. Okay? So you can look at, because the point is that here you're only getting, in this moduli space, you're only getting hyperelliptic quartics which are double covers of a smooth quadric. Okay, you're missing all hyperelliptic quartics which are double covers of a cone. So what you should do, you look at all quadrics, and you look at the projectivization of a natural rank 2 vector bundle. So over a quadric, what you get is the projectivization of H0 OQ of 4. Okay? But now this is P, I mean, this, the pick of this is 2. Okay? So you naturally, so now when you want to take a GIT quotient, So the group now, of course, the group now will be PGL4. Okay, so you want to take P of E modulo PGL4, but you have to choose the linearization here. And so you have a parameter, choose linearization. Okay, and if for certain extreme values of t, you will get this GIT moduli space in which you don't see double covers of cones, but as you vary t, you will see double covers of cones which become stable, and so on. And so you can make a variation of GIT, and if you're sort of adapting what was done by Casalina Martin, Radulazza, and I will forget the other. Who? David Jensen. They studied the case of 3-3, the divisors of 3-3. You can certainly prove part of our predictions for F18. You can actually prove. And so, of course, the idea would be maybe one can do, if one is strong enough with VGIT, maybe one can do a lot more. Okay, thanks.